Welcome to the second module on parenteral dosage form, and I hope you remember that in our last module we discussed about introduction of parenteral dosage form, its advantages, disadvantages, properties of parenteral dosage form, different routes of administration of parenteral dosage form and pre-formulation parameters of the same. And in this module we will be discussing about formulation development of parenterals. And after completing this module, you will be able to understand important steps involved in parenteral production, component of parenteral formulation, methods of preparation and properties of water for injection, importance of tonicity and methods of its determination. And we will be covering formulation of parenterals, different steps in development of formulation, production for water for injection, formulation component, different types of vehicles which are used in development of parenteral dosage form and other added substances and methods of determination of isotonicity. So, as you know that the aim of formulation development of parenteral dosage form is to produce safe, effective and stable product, and the component which is present in the higher proportion is the vehicle, or we can also call it as a solvent. And the vehicle used for parenteral must be sterile, it should be free from pyrogen and should be free from any particulate matter and should be isotonic with blood plasma. So, before we move further, let us have a look on the general steps for production of parenterals: cleaning, preparation of bulk products, filtration, filling and sealing of ampoules or vials, and sterilization, and finally we go for test for quality control. So, these are the general steps which is followed in the manufacturing of parenteral dosage form. Now, what are the vehicles which are used in the development of parenteral dosage form? We can classify them as aqueous and non-aqueous vehicle, and most commonly we use water for injection and sterile water for injection as an aqueous vehicle for preparation of parenteral dosage form. So, as per United States Pharmacopoeia, water for injection. So, this is the verbatim definition of water for injection. Water for injection is intended to be used as a solvent for preparation of parenteral solution subject to final sterilization. We use suitable mean to minimize microbial growth or first render it sterile and protect it from microbial contamination. And sterile water for injection is water for injection sterilized and suitably packed. It contains no antimicrobial agent or any other added substance, used as a solvent for parenteral products such as sterile solids that must be distributed dry because of limited stability of their solution, and it must be packed only in single dose container of not larger than 1 liter in size. Now, moving to non-aqueous vehicles for parenterals. Generally, fixed oils are used as a non-aqueous vehicle and it must be of vegetative origin, so that it will metabolize and will be liquid at room temperature and will not be rancid. It should qualify certain limit as per United States Pharmacopoeia for fatty acid content, for iodine and for its saponification value. The oil most commonly used are cottonseed oil, corn oil, peanut oil and sesame oil. Fixed oils are used as a vehicle for certain hormones, for example, testosterone, progesterone and deoxycorticosterone, and certain vitamins like vitamin K and vitamin E preparations. Now, moving to methods of preparation for water for injection, distillation and membrane technologies. These are two methods which are used for preparation of water for injection. European Pharmacopoeia permits distillation as a method for water for injection, and USP and JP, that is United States Pharmacopoeia and Japanese Pharmacopoeia, it permits also other methods of preparation for water for injection. Water miscible vehicles, these are co-solvents like glycols, for example, PEG and PG, glycerol, sorbitol and ethanol. These are miscible with water and have been used as a small portion of the vehicle in the formulation of parenteral dosage form. For example, ethanol, that is ethyl alcohol, which is used in solutions of cardiac glycosides and glycol, which is used in solutions of barbiturates. And this co-solvent must be used carefully as to maintain the integrity of product in terms of safety and stability. Now, moving to distillation, it is a process of converting water from a liquid to gaseous form, and since steam is pure gaseous water, so all the contaminants in the feed waters are removed. As you can see in the diagram, a conventional still which consists of a boiler or evaporator which is used to evaporate the feed water or distillant, source of heat to vaporize the water, an appropriate head space is necessary above the level of feed water with condensing surface for reflexing the vapor, thereby returning the non-volatile impurities to the feed water, and a condenser for removing the heat of vaporization, thereby converting the water vapor to liquid distillate. And there are two types of water for injection distillation units, vapor compression still and multiple effect still. Vapor compression still, in this method the feed water is heated to boil by applying external source of heat, then the vapor is produced and it is separated from the entrant feed water and led to the compressor that compresses the vapor and increases its temperature approximately to 107 degrees centigrade. Then it passes through the steam and condenses on the outer surface of the tubes to get the distillate, and the heat which is released at the time of condensing the vapor is utilized as a source of heat to boil the feed water in the second cycle. So, this is all about vapor compression still. Now, moving to the advantages of vapor compression still, it needs low energy consumption and there is no need of cooling water to condensate the pure steam, and no need of high quality inlet water, and there is no need to pressurize the inlet water. This process is extremely safe with no risk of any cross contamination through plant steam or inlet water and reduced maintenance. And there is a disadvantage of this method, that it needs a high electric demand. Moving to multi effect still, in this method phase changes of water takes place. As you can see in the diagram, a series of up to 7 stills can be used, with the first effect operated at highest pressure and the last effect at atmospheric pressure. Steam from external source is introduced only in the first effect to evaporate the water, and the exit steam which is used as a source of heat for second effect. The vapor is condensed to get the distillate in each effect, and this process is continued till the last effect is reached. Now, moving to reverse osmosis. As shown in the pictorial depiction of reverse osmosis, it is a selective reverse permeation of molecules through a semi-permeable membrane separating two aqueous solutions of different concentration, and a driving force usually between 200 to 400 psig is required to overcome the osmotic pressure and to permeate pure water through the membrane. Reverse osmosis, in this method the RO membranes which are used are made up of cellulose acetate or polysulfone coated with aromatic polyamides, and sometimes passage from two membrane in the series is used to increase the efficiency of removal of the small molecules. This also decreases the risk of structural failure of a membrane to remove the other contaminants such as bacteria and pyrogens. Sometimes both RO and distillation systems are used simultaneously for generation of high purity water, since raw water which is having greater impurities can contaminate the distillation unit and affect the operation of a still. So, the raw water is first run through the RO unit to eliminate the contaminants. Ultrafiltration, this is the modification of reverse osmosis, and it is a type of membrane filtration in which hydrostatic pressure forces a liquid against semi-permeable membrane, and in this method solids and solutes of higher molecular weights are retained and solids of low molecular weights are passes through the membrane. So, in principle ultrafiltration is not different from reverse osmosis except in terms of size of molecules which are retained. Storage and distribution of water for injection. So, as per United States Pharmacopoeia, water for injection should be stored at 80 degrees centigrade to avoid any type of contamination, and as the water cannot be used as 80 degrees centigrade, so heat exchangers must be installed to reduce the temperature at the point of use. The USP also permits the water for injection to be stored at room temperature, but not more than 24 hours, and it requires frequent sanitization to reduce the risk of viable microorganism. Water for injection is stored in stainless steel tanks, and these tanks are connected to the welded stainless steel distribution loop supplying the various sites with a continuous circulating water supply. The tank is provided with a hydrophobic membrane vent filter capable of excluding bacteria and non-viable particulate matter. So, as per United States Pharmacopoeia, there are certain acceptance criteria for water for injection, as it should be clear, colorless, odorless liquid with total organic carbon of not more than 500 ppb, that is parts per billion, and conductivity at 25 degrees centigrade should be less than 1.3 millisiemens per centimeter, and limit for bacterial endotoxin should be less than 0.25 EU per ml, that is endotoxins unit per ml, and the pH of water for injection should lie between 5 to 7. So far we have discussed different methods of preparation of water for injection: vapor compression steel, multi-effect steel, reverse osmosis, ultrafiltration, and specific criteria for storage and distribution of water for injection, as well as the specified limit for acceptance of water for injection as per United States Pharmacopoeia. Now, moving to isotonicity. It is the most important parameter with reference to parenteral dosage form. The parenteral product should be isotonic with blood plasma as to avoid any pain and discomfort or any kind of swelling and contraction of blood cells. 0.9% of NaCl is said to be isotonic, and it is used as a standard for pharmaceutical preparations. Now, we will see different methods of adjusting isotonicity. There are two classes of methods. In class 1, we will be discussing about freezing point depression and sodium chloride equivalent method, and in class 2, we will be discussing about White-Vincent and Sproul method, or we can also call it as a modified White-Vincent method. In freezing point depression, we will be adding any substance to lower the freezing point of solution to minus 0.52 degree centigrade. Why we are using minus 0.52 degree centigrade? Because it is the freezing point of blood and tears, and as we all know that parenteral product are administered directly into the blood circulation, so it should be isotonic with blood plasma. So, any solution having freezing point equal to minus 0.52 degree centigrade is said to be isotonic. The formula used for calculating the amount of adjusting substance to make isotonic solution is weight percent is equal to 0.52 minus A upon B, where weight percent, that is W percent, stands for concentration, that is in gram per 100 ml of adjusting substance. A stands for freezing point depression of 1% of unadjusted substance, and B stands for freezing point depression of 1% of adjusting substance. So, as you can see in the example, which shows that by putting the values of A and B, we can calculate the weight percent of adjusting substance required to make isotonic solution. In the second method of class 1, that is NaCl equivalent method. NaCl equivalent, E, is the amount of NaCl that is equivalent to 1 gram of drug, or it has the same osmotic effect as 1 gram of drug. So, this method is used to calculate the eNaCl in the first step, and in the second step we will be calculating the amount of NaCl to reach 0.9% of its concentration. So, in step 1 we will be calculating eNaCl value, which is generally given to you in the question, and if it is not given, it can be calculated by using this formula ENaCl equal to 17 L-iso of drug divided by molecular weight of drug. What is L-iso? L-iso is a constant factor based on isotonic concentration of drug molecules. In step 2, we will be calculating the amount of NaCl to reach 0.9% concentration, and the formula which is used is W percent or weight percent is equal to 0.9 minus drug in percentage multiplied by ENaCl value, and ENaCl value as I also mentioned earlier, it is given to you in the question when you will be attempting example for calculating isotonicity, where W percent stands for weight of NaCl in gram per 100 ml to make isotonic solution. Drug percent is equal to weight of drug in gram per 100 ml ENaCl, NaCl equivalent weight to 1 gram of drug. So, as you can see in this example that how we have calculated the amount of NaCl added to 100 ml of water to make isotonic solution. Now, moving to the third method, that is White-Vincent method. In this method, we will be adding the water to the drug to make isotonic solution and adding the isotonic vehicle to bring the final volume or to make up the volume to the required amount. So, there is a straight formula for calculation of the adjusting substance. So, in this we will be using water. So, V, that is volume of water, is equal to W multiplied by ENaCl multiplied by 101.1. This 101.1, it is a constant which is calculated by dividing 100 to 0.9, and V stands for volume of water and W stands for weight of drug. As you can see in this example that how we have calculated the volume of water which is required to make isotonic solution. Moving to Sproul method. So, Sproul method is a modified White-Vincent method in which the total volume is kept constant to 30 ml and the drug concentration is kept constant to 1%. So, that the amount of drug will be 0.3 gram and it will be constant. So, it was done to make easy for practicing pharmacist, and rest of the formula is same as we did in White-Vincent method. So, Sproul method is we can also say that it is modified White-Vincent method. So, rest of the calculation will be same. Now, moving to the additive or excipients used in formulation of parenteral dosage form. So, we used antimicrobials, antioxidants, buffers, chelating agent, protectants, solubilizing agent, surfactants and tonicity adjusting agent. Antimicrobials we use to protect our preparation against growth of microorganisms, and antioxidant, chelating agent and buffers. These are used to enhance the chemical stability of a solution. Protectants, it prevents the loss of activity of drug caused by stress or by adsorption. Solubilizing agent, it increases the solubility and maintains the drug solubility. So, there are numbers of methods which are used to improve the solubility. Surfactants, this enhances the physical stability of especially in case of proteins. Tonicity adjusting agent, it provides patient comfort and it reduces the pain and discomfort at the site of administration. So, these are the additives which are used, and I suggest you to refer the more examples for these additives and excipients, and they are used in their specific concentration. So, please go through from the examples. So far we have studied different vehicles for development of parenterals, including aqueous, non-aqueous vehicles, water miscible vehicle, different methods of preparation. We have covered vapor compression still, multi-effect still, reverse osmosis, ultrafiltration, isotonicity and methods of its determination. Please refer more example for better understanding of isotonicity, and in the coming module of parenteral dosage form, we will be discussing the different types of parenteral preparation and please go through from the suggested further reading and do take part in our discussion forum if you have any query regarding the content of this module, and thank you so much for being with us.